Hello guys, welcome back to another video. So for this video I will be looking at principal components analysis and how to interpret principal component values. Principal component values are generally hard to interpret and most persons tend to go for graphical interpretation. However, in this video we'll be doing both. Now let's load a few package first. So we're going to load the factoextra package. We're going to load the ggplot2 package, and we're going to load the corrplot package. Now I already have a data set which I'll be using for this example, and that data set is called diab.txt, and we're going to load in our data set. Now let's take a look at the head of our data set. So in this data set we can see that we have attributes: pregnancies, glucose, blood pressure, skin thickness, insulin, body mass index, diabetes pedigree function, age, and outcome. Now this data set represents some females. Information was taken on some females with different attributes, and the outcome represents persons who had cancer. So 1 would represent a person with cancer, and 0 would represent a person without cancer. So now let's go and view the dimension of our data set. So we can see that we have 768 observations and 9 attributes. So now we're going to run our principal component function on the data set. So we say diab.pca is equal to prcomp diab on the data set, and scale is equal to true. Now when we say scale is equal to true, what we're saying that we'll need to use the correlation matrix to calculate the principal components. If we had said scale is equal to false, then what R would do is use the covariance matrix rather to calculate the principal component values. Now we need to understand the difference between using the correlation matrix and the covariance matrix. So we use the covariance matrix when the units of measurement of all our attributes are the same, and we use the correlation matrix when the units of our attributes are different. So now let's run our principal component on the data set. Also, let's look at the possible things that we can get from running our principal component. The different type of variables that we can see. So from this principal component analysis, the different results that we can obtain are the coordinates for the variables, the correlations between variables and the dimension, the CO2 values for the variables, that is how well is an attribute represented in each principal component's value, or represented in each principal component, and the contribution of the variables. So how well does each variable or attribute contribute to this principal component. And now let's take a brief look at our eigenvalues of our principal component. So we can see that for dimension 1, which is principal component 1, the eigenvalue is 2.352, and the variance percent is 26.1, indicating that dimension 1 accounts for 26.139% of the total variation within the data set. Now up to dimension 4, or let's just say up to dimension 5, the cumulative variance percent is 77, indicating that the first 5 principal components account for 77.5% of the total variation within the data. Now let's look at a plot. This is a scree plot of our principal components, and it shows the percentage variance for each principal component. So we can see that the first is 26.1%, 19.7%, 12%, and 9.8%. Now we can see that if we're comfortable enough, we can probably stop at dimension 3. And in this example, I am just going to stop at dimension 3 with 58.3% of the total variation being explained. Now, if we should plot the contributions, so we want to see what contributions are greatest in dimension 1. So in dimension 1, we can see that glucose, the outcome if a person has diabetes, and the body mass index and insulin contributes the most to principal component 1. Now, if we should take a look at principal component 2, we can see that age, pregnancy, skin thickness, and insulin are the main contributors, increasing the total variation in dimension 1. Now, if we look at dimension 2 or principal component 3, we can see that the third principal component rather, blood pressure, outcome, glucose, are the main contributors in dimension 3. Now we're just going to skip dimension 4 since I would assume that you guys get the gist. Now if we should look at a corrplot of the how well is each variable represented in each dimension. So here we have a correlation plot, and in dimension 1 we can see that glucose, the body mass index, the outcome are well represented, and insulin are well represented. We can see that in dimension 2, pregnancies, skin thickness, and age are well represented in dimension 2. So basically what this is saying is that dimension 2 is a good representation of pregnancies, blood pressure. Dimension 2 is a good representation of pregnancies, skin thickness, and age. So dimension 3 is a good representation of blood pressure, and dimension 4 is a good representation of the diabetes pedigree function. So basically what we can take from this is that the main variables that we should look at when we are interpreting the first principal component is glucose, the body mass index, the insulin, and the outcome. Now let's look at the principal component values. Now this might look a bit messy for persons to understand and try to analyze. So persons tend to use graphical methods to interpret their values. Now if we should look back at principal component 1 and look back at the contributions that was made to principal component 1 again, we can see for principal component 1, the greatest contributions that were made was glucose, outcome, body mass index, and insulin. Now, interpreting principal component 1 from these principal component values, we're going to look at the glucose values right here, which is minus 0.436. We're going to look at the outcome values, which is minus 0.4156. We're going to look at the body mass index, value, which is 0.397, and we're going to take a look at the index, the insulin, value, which is minus 0.336. Now, what this is saying is for a decrease in glucose and a decrease in the body mass index and a decrease in insulin intake, we see a decrease in the outcome of persons having diabetes. So now for principal component 2, let's look at the contribution of variables. So for dimension 2, the contribution of variables are age, pregnancies, skin thickness, and insulin. So interpreting principal component 2, we're going to see that for a increase in age, as we can see that age is positive, for an increase in age and an increase in the number of pregnancies, we see a decrease in skin thickness. We have a decrease in skin thickness and a decrease in the number of insulin intake. So basically these values, these variables are correlated in some way. So either when we have an increase in one, we have a decrease in the other, or when we have an increase in both, we have a decrease in the other two. Now we're just going to analyze principal component 3 as the final one, so we can just load the contributions of principal component 3. So here are the contributions of principal component 3. We have blood pressure, outcome, and glucose. So blood pressure, if we take a look at blood pressure, we can see that blood pressure is minus 0.629, and outcome is positive with a 0.3946, and the glucose is also positive with a 0.3914174. Now what this principal component is saying, that there's a relationship between blood pressure, outcome, and glucose. Their glucose level tends to go up when their blood pressure comes down, and that is basically an interpretation of the principal component values. Thank you very much for watching.